This week, we'll finish the topics about arrays and loops. And let's now do another computational problem about whether an array is sorted or not. And there's some terminology I would like to clarify, which you will see very often in computer science discipline. Okay, let's see what the problem is. Given an array, let's say A, of integers, how do you determine if it is sorted in a non-decreasing order, or people say non-descending order? So there are four possible sorting orders of a given array, which I would like to clarify as much as possible. Okay, let's now do this first. So there are four cases over here. Let's talk about, in general, you're given an array A of integers, let's say, and then the first element will be index 0, and the last element will be a.length minus 1 index, right? And we talk about any adjacent elements, any adjacent ones. Let's talk about I and also j. Of course, j will be a larger index than I, but they are adjacent to each other. Or you can think about j is equal to I plus 1. All right. So there are the four cases you have to worry about. Let's do it systematically, so it wouldn't be too tricky for you. Okay. The first one, let's talk about decreasing, or interchangeably we can say descending. So that one there is very easy. Just give you one example. Decreasing simply means you will go, for example, 4, 3, 2, 1, 0. Okay, you're strictly decreasing. And let's now just define mathematically very quickly. So when we say decreasing, so decreasing simply means for any adjacent indices I and j in the array, it should be that ai is actually strictly larger than aj. So basically you go like this. If this is ai, it should go to aj, should be strictly decreasing, right? So now let's make it more general. If I say an array is sorted in the decreasing or descending order, what does that mean? So look at this diagram over here. So we got the horizontal axis, it will be the indices. So we basically go from left to right, right? So in the smallest index into largest index. And also the vertical axis will be the value. Let's see how the diagram should look like. In the case of a decreasing order, it should be exactly this. Okay, and now if you look at, if this is ai, and let's say this is next one, aj, you can see that should be strictly decreasing. Okay, so that's easy to see. And what about increasing and ascending? That will be symmetric. So when we talk about increasing or interchangeably ascending, so let's define that mathematically first. So when I say ascending or decreasing, ascending or increasing, sorry. So that will be ai should be strictly less than aj. For example, we can have 0, 1, 2, 3, 4. And what about the diagram? It would be exactly this. Another very obvious property for you, let me just mark it. Let's say this may be ai. And aj, the adjacent indices index, so aj here, so you can see is definitely increasing in this way, right? In the case of the array is sorted in the decreasing order, you will know that the first element must be the maximum elements, and the last element should be the minimum elements for sure. Symmetrically, if you say an array is sorted in the increasing or ascending order, the first element at index 0 should be the minimum elements, whereas the last elements should be the maximum elements, right? These are very straightforward to see. The more tricky ones will be the next two. The next two cases, either non-descending or non-ascending. Okay, so when we say non-descending, we can also say non-decreasing. When we say non-ascending, we can also say non-increasing, right? So we can also always use ascending and also increasing interchangeably, and also decreasing and descending interchangeably. Okay, what is really non-descending? You can think about the English word non here is like a modifier. It's simply like a logical negation. Okay, so we can really apply the logical law that we actually spoke about. Okay, let's see. Let's do the math first of all. When we say non-descending, right? Non-descending, you can see descending is exactly over here. So when we say non-descending, it will be not the case. Descending, ai larger than aj. So this means as long as it is not descending, we will be okay, right? So it would be applying the logical law for the logical negation. So it would be AI less than or equal to AJ. So how does the diagram look like? It would be something like this. You can, as long as you're not decreasing or descending, you're okay. So you can either be increasing or stay the same. You can be either, let me draw better. You can either be increasing, stay the same, increasing, stay the same, increasing. As long as you are not decreasing, you will be okay. Okay. So for example, you can see this could be AI, and this could be AJ. In that case, you're really talking about the equal case over here. And or alternatively, this could be AI, and the adjacent index would be AJ over here. So this is really talking about the strictly less than case over here, right? You got two possible subcases for non-descending. All right, example, it could be, let's say 0, 1, 1, 2, 3. You can see when we go from 1 to 1, it's pretty much like going from here to here. When you go from 1 to 2, it's like going from here to here, right? For example. Okay, finally, we apply the similar reasoning here. What about non-ascending over here? Non-ascending, let me use a different color. Non-ascending simply means it is not the case that it is ascending. Okay, so non-ascending, which means it might stay the same or decreasing. So ascending is exactly over here. So not the case, AI less than AJ, which will be equivalent to AI larger than or equal to AJ, right? So now, how about the diagram? As long as we are not ascending, we'll be okay. So meaning that you can either be decreasing, stay the same, decreasing, stay the same, decreasing. As long as you are not ascending, you will be okay. Okay, and you can see. Let's just see one example. It could be 3, 2, 2, 1, 0. That would be another case, right? You can see over here. For example, this could be AI, and this could be AJ. So this will be basically AI strictly larger than AJ. So this will be the larger than case over here. And also, this might be AI, and this might be AJ. So this will be the flat case. So this will be the equal case over here. All right. So that's about these four cases. Hopefully, it's very straightforward for you. Let me mention one more thing. When you compare decreasing versus when you talk about decreasing and also non-ascending over here, when you talk about these two, you can see the diagram here is strictly decreasing. This one here, decreasing sometimes will stay in the flat. One is the special case of the other, but not vice versa. But how do we know, right? So you can think about, let me write down the answer for you. You can think about this. Can I say, whenever I say the array is sorted in the decreasing order, is it at the same time sorted in the non-ascending order? Is it the case? The answer is yes. Because you can see over here, is simply you can think about this diagram over here is simply a special case where we simply just got all the decreasing. We just don't have any staying the same, like a flat case. So that's why. However, not vice versa. Can I say, for example, over here, can I say this case is also decreasing? The answer is I cannot say that because, for example, you can see this will be a violation. This will be a violation for strictly decreasing. They simply stay the same, right? You can see the non-ascending simply allows for equal over here. All right. Similarly, we can also compare this case and also this case over here. So one is the special case of the other, but not vice versa. But exactly what? Exactly how? Let's see this. Let's say for this one here, can we say that whenever we say the array is sorted in the increasing order, is also sorted in the non-descending order? The answer is yes. Non-descending. Okay, the answer is yes. Because you can see here, it's simply a special case. We simply just got increasing all the time, right? We just don't have the stay the same, right? In this case, right over here. So we can say this is a special case of this, but not vice versa. Why? Let's see. let's use this color here. So now, can we say that this is actually increasing or descending or ascending? Can we say this is increasing? The answer is no, because you can see these two are the violation, right? So these two are not really strictly increasing. These are strictly increasing, but not these two. So these two are the violation, these two. All right. So guys, I think that's really about some very thorough and systematic introduction about these two sorting orders. They are not difficult, but I think you just have to know whenever the problem itself might just use these words in English, but it should really directly link to their corresponding mathematical relations over here. And of course, for these two, the best way to understand them will be to apply some logical property for the negation. All right, let's now go back to the slide over here. So now, how do we solve this problem here? When we want to sort, when we want to check if the array is actually sorted in a non-decreasing order. Let's look at the solution. To solve this problem here, let's first identify the non-decreasing order requirements. So that means either you can increase or you stay the same, right? So that would be the one of the cases that we just spoke about. Okay, you can just keep that in mind. And let's see some example here. You can see 1, 2, 2, 4 should be true. It's actually sorted in a non-decreasing order. You can see from 1 to 2 it's actually increasing, and also from 2 to 2 it stays the same, and 2 to 4 is also increasing. On the other hand, for this array over here, as soon as you can find some violation witness, it will be false. What's the violation witness? It will be index 1 and index 2. You can see from 4 to 3, it's actually decreasing, which will violate the non-decreasing requirements. All right, so how do we solve this? So there are two solutions over here. Let me show to you right away, and then I'll trace the second version together with you, and hopefully you'll be enough for your learning. Version number 1, we can simply, I will explain this in a moment about why it would be a.length minus 1 rather than a.length. The critical factor is really we're not just using I, but we're also using I plus 1 in the body of the loop. That's the main critical factor, but I'll explain that. So that'll be version number 1, which means we always scanned almost the entire array from the first, index 0 until the second last index. So that's something I'll visualize to you. Okay, that's version number 1. So there's no early exit, meaning that if you find a violation witness earlier in the array, you still cannot exit. You always got to scan through the entire array. So that's kind of the version 1 that we spoke about in the previous is all positive example. So version number 2, in order to really cause early exit, so in that case, we'll put the is sorted over here as part of the state condition. As soon as the is sorted becomes false, we're actually going to exit from the loop, right? That's exactly similar to what we did before. And also, since we are checking the universal property, we want to make sure all the adjacent indices will actually satisfy the non-decreasing order requirements. So that's why we should really initialize this to be true, right? What will be the consequence if you initialize that to be false? That's one question for you to think about, right? We also explained that also previously. All right, so let's now take a look at the version number 1. I'm just going to show you the slides, give you a little bit guidance about how to read the trace table, but I'll trace version number 2 together with you. Okay, for version number 1, we're going to scan through the entire array. So let's now take a look. So the trace table, so we start with I being 0. And then I would be, for the first iteration, it will be 0, right? And then also, let me just show you the entire table, and I'll highlight to you the critical points you should really watch out for. Okay, so that'll be the entire trace table. You can see when I is equal to 0, so that means we have to compare A0 and A1. So what's A0 and A1? So this will be A0 and A1, so that's 1 and 2. And then in the second iteration, I will be 1. So that means we should really compare A1 and A2. So A1 and A2 are these two elements. And in the third iteration, we should really compare A2 and A3. So A2 and A3 should be 2 and 4. So that's why, right? You can see so far, we have maintained the less than or equal to, that's the non-decreasing order that we are requiring, right? And then we're simply accumulating, it's sorted using conjunction. Right? So now you can see why we should really use a.length minus 1. What's a.length? A.length is 4 in this case. If we simply use a.length, hypothetically, let's say we don't have the minus 1 over here, only strictly less than a.length. strictly less than 4, so that means we can still go for I being 3. In that case, if you imagine there's another extra row over here when I is equal to 3. So that means we should go for A3 and also A4. Is there any A4 for this array? The answer is no. So that's why it should be strictly controlled to be A.length minus 1. It's really important for you to note. That's something I will try to emphasize again when I visualize version number 2. All right, another case for version number 1. Let's say this is 2433. Apparently, you can see this will be some violation witness, and this is only about halfway through when we scan through the array from left to right. However, this version number 1, since we didn't put any extra condition here for the state condition, is not going to early exit. Okay, let's now, if you look at the trace table over here, let me go all the way to the end. You can see over here, it's really important to note. After this iteration, I is equal to 1, so that means we're going to check A1 and A2. From 4 to 3 is going to violate less than or equal to, right? 4 less than or equal to 3 is definitely going to be false. So that's why this will be false, and it's sorted is going to be accumulated with false, so it will become false. At this point, we should be able to exit from the loop right away, because we know that for universal property, once you see the violation witness, you should be able to exit. But for this version, first version here, even though it is correct, but it's not as efficient as if we can have early exit. So that's about version number 2, which I'll speak to you about. All right, guys, I hope version number 1 is okay for you. You can definitely try to trace it visually like how I did it for the previous example. But now for version number 2, I'm going to trace it together with you quickly, just using 2 example test cases. Okay, for version number 2, okay, over here, let's say the first case I would like to trace is the array itself. If you look at that, 1, 2, 2, 4. So we know that it's actually sorted. So that means you will not be able to find out what the you can never find any violation witness, because this one simply satisfies the property. So we will still unavoidably still have to scan through the entire array. Let's do that very quickly, right? So now I want to say this very explicitly for you. We know that A.length in this case will be 4, right? We got 4 elements in the array. 4 minus 1 will be 3. So that means I is going to be strictly less than 3. I will be 0, 1, and also 2. So these are the only 3 values that we're going to use, right? More precisely, you can think about for the very first iteration, when I is equal to 0, we are actually going to check 0 and 1. And when I is equal to 1, we are going to check to see 1 and 2. And then when I is equal to 2, we're actually going to check to see 2 and 3 over here. You can see every time we only check the adjacent indices. However, that's why if you actually say hypothetically, if I got rid of minus 1 over here, that means I might still have 3 over here. But the problem is it will be 3 and 4. So now 3 and 4, do you have A4? No, you don't. So that's why we should not we should not get rid of the minus 1 over here, right? Let me put it back. So that's the point I would like to say. All right, and then the rest is pretty straightforward. If you now just try to see this, so now 0 is gonna check to see 1 is less than or equal to 2, 1 less than or equal to 2, and also when you check to see when it's equal to 1, so 1 and 2, so 2 less than or equal to 2, that's also true. And also, let's say when I is equal to 2, so in the indices will be 2 and 3. So now 2 less than or equal to 4, that's also true. You can see true, true, and true. So that means the result will just be true eventually. Right? This case is easy. Let's see the second case. Let's see how early exit might happen if you find a violation witness on the halfway through. Let's see exactly. So we still got the same array over here, the same size. The size will just be 4. 2, 4, 3, 3, which means when we actually get to this particular iteration, when I is equal to 1, in that case, we're going to find a violation. Let's see exactly how. So I is going to be 0, 1, and 2. Okay, remember it's going to be A.length minus 1. 4 minus 1, which will be 3. Right? So 2 is strictly less than 3. And then we're going to see this. So for, let's be consistent here. So I will be 0. So we check index 0 and index 1. So that'll be 2 less than or equal to 4. So 2 less than or equal to 4. This will be true. No problem. And then let's try to see the green one. Okay, let's say when I is equal to 1. So that means we're going to check to see index 1 and 2 over here, right? For the second iteration. And then it's going to be 4 less than or equal to 3. And that one there is going to be false. Okay? That means at the end of this particular iteration is sorted at the end of the second iteration more precisely. Is sorted is simply just going to be false. So when you go back to check to see if you should really go for another third iteration, is sorted will just be false. Meaning that this conjunction here will just be false. So we don't really go for the third iteration, right? And that's it. And then we're gonna exit after this particular iteration. That's how the early exit can actually happen. So you can either use version number 1 or you can use version number 2. But version number 2 is definitely more efficient if the array size is very large and also you find the violation witness on the halfway through. That's the principle. All right, so that's about the sorted problem here. Let me just go over the rest of the some slides and then we'll finish the current video. Okay, so that's exactly the example I just spoke about. You can also refer to the slides as well. Okay, so now I would like to summarize about checking universal properties versus existential properties. So far we have seen is positive or is some number positive and also is sorted. We have seen 3 examples already. So now let me generalize them. Universal property simply means we want to check to see if all the elements satisfy a property, right? And then we need to use conjunction to solve it. And then approach number 1, you may just scan through the entire array. You can see from index 0 to index 0 to the last index. But in the sorted problem, we have to say a.length minus 1 because in the body of the loop, you may want to use I plus 1. Sometimes you may want to use I minus 1. So you want to adjust the state condition accordingly. So that's something I'll leave to you. But the principle is you want to scan through the entire array almost. And approach number 2, you can do early exit if possible. The principle will be as soon as you find some element that does not satisfy a property, which means a violation witness. In that case, you're going to exit from the loop, right? You can see here. And also we initialize the Boolean variable to be true, right? That's a quick summary. And then if you can do the tracing if you like, that's simply the all positive example that we did previously. You can do the tracing. I'm not going to bother you with that. However, 2 questions that we spoke about before, you always want to think about. Why the all positive Boolean variable should be initialized to be true. That's something we spoke about. And also, what if I simply, let's say we simply change the condition over here. Let's say we get rid of this part over here. So we still scan through the entire array, but we don't have any accumulation. That's basically version number 2 that we spoke about, right? And that one is actually wrong. Why is that wrong? You can think, can review the notes that we spoke about. Okay, that one has been explained already. All right, what about existential property? Everything will just be symmetric. So now rather than checking that all the elements should be satisfied in the universal case, so now in the existential case, at least 1. As long as 1 element in the array satisfy the property, that will be okay. That will be we should return true. Otherwise, it should be false. Is there at least one negative element, for example? And then approach number 1, still 2 approaches. Okay, let's see here. For approach number 1 and approach number 2, we have to initialize the variable to be false. So false is the identity of this junction, which we spoke about. And then the state condition will be similar. You can see in the case of the early exit version, we'll say we have not found any satisfaction witness. In that case, as soon as we find one, we'll set the found negative to be true. In that case, not true is going to be false, which will make the conjunction false, right? That's also something we traced in detail previously. So now it's only a summary. So the idea would be as soon as we find an element that satisfies a property, so that is the satisfaction witness, and then we're going to exit from the loop. All right, so nothing new. It's always nice to reinforce, to review quickly. And then, so that's another example here. And then we, after the tracing table, always there's another 2 questions I want to ask you. Number 1, why do we have to initialize this to be false? What if we make it true? That's question, right? And the short answer is false is the identity for disjunction, which means it's not going to affect any result on the other operand. That's something you can review from the previous recording, the previous week. And also, what if we get rid of this part over here, we only leave this part over here. However, we don't really try to accumulate the result. And why is that wrong? Again, that's the version number 2 that we spoke about in the previous week. Okay. All right, final remarks. What about checking array properties, either universal or existential? Sometimes you may just have to reiterate through the entire array, right? That's not really the universal versus existential problem. So here, for example, if you want to calculate maximum, minimum, total, the sum of the array, so this is not really belonging to either universal or existential problem. So here you have no choice but to scan through the entire array. On the other hand, if that's either universal or existential, then you can really code the early X version. So for example, for the universal, we know that if we want to know if all the numbers are positive, you can certainly return false as soon as you find out the violation witness. And also, if you want to solve the existential problem, okay, you can see at least one negative number. In that case, as soon as you find out the satisfaction witness, if as soon as you find that, you can exit from the loop, right? That's something we have explained as well. All right, so we are going to go. We already finished the topic about universal versus existential problem, and now we're going to talk about short circuit applying guarding the array indices.